Okay, looks like it's working. Welcome to the last session of SummerSOC, and I must admit that I'm kind of happy to be, chairing the last session of the topic of sustainability, because it allows me to make a joke. Because sustainability as a topic, everybody says it's very important. It's been continuously mentioned that, okay, global warming, this, that, and whatever, we have to do everything more sustainable. But in all places, it's always come last. All the other important topics gets attention, and then sustainability, yes, sustainability also. To make it clear, just a joke. But I think it's a very real one, and I hope that Brian today will convince you that, first of all, the challenges and importance of the topic even higher than you may probably imagine. Even it's already high, but it's even higher from one side. And from the second, that research challenges are interesting and requires quite a lot of work still to be done. And I hope that after today's presentation, you'll feel like, yeah, I would like to contribute to that topic. But having said that, Brian, please enlighten us about sustainability.
Well, thank you, Alexander, for the kind introduction. Today I'll be talking about sustainability at scale and how we can achieve this and how far along we are already in the process of being able to achieve the sustainability at scale. But first, I want to talk a little bit about who I am, because I see a lot of new faces here today, also see some familiar faces. So let's start with that. After that, I'll give a brief introduction to the topic of sustainability in general, have a look at where we are on a global scale with sustainability, and then I will dive a little bit into what we do at the Digital Lab, which is the team that I lead. And then we look into 2 publications that we had this year on the topic of sustainability at scale. So, let's start with a short introduction. I'm Brian Setz. I'm the team lead of the Digital Lab. We are a team of engineers and educators that focus on bringing innovation to the university's curriculum at the University of Groningen. I got my PhD in computer science in 2022 at the University of Stuttgart. And a topic that's always been very close to my heart is sustainability. It's been following me around everywhere, and it's no different now. My first encounter with sustainability was at 2 European projects called Setz and Indiana. These were focused on sustainability in buildings, specifically residential buildings. These projects focus on creating IoT gateways, one of the first IoT gateways, using OSGI, a technology I hadn't heard of in a long time until Christian Becker brought it up in the beginning of SummerSOC. It was nice to hear that again. Then in 2012 and 2014, I worked on 2 University of Groningen Green Mind Awards. These were awards given to employees and students of the University of Groningen when they had a great idea regarding sustainability. The first project focused on a building that was an office building. It focused on waste separation. It focused on optimizing the lighting control of the building. It had a lot of different facets. And then the second project, it was more about the heating system of a building. So how can we optimize the heating in a building to make it more efficient, control it more efficiently. Then in 2015, I got my own sustainability grant, which we used to create a competition between buildings. We had multiple buildings that were participating in the competition, where the goal was to reduce the carbon footprint of the buildings. And then buildings could be compared to one another and see how they're doing in relation to each other. Then the year after that, based on all the lessons learned in the previous years, I was one of the founding shareholders of Sustainable Buildings, a company that focused on energy monitoring, carbon footprint monitoring. Then at the same time, I started my PhD project, Next Gen Smart Data Centers. This time the topic was not buildings, but data centers. Then in the last 2 years, I've been working on 2 sustainability accreditations for dry labs. So the digital lab, the lab that I lead is a dry lab. And we were the first dry lab at the University of Groningen to achieve these certifications. LEAF is the laboratory laboratory efficiency assessment framework, and Green Disc is the successor of LEAF. So I started with residential, I moved down more towards offices, then for a while data centers was my topic. But now I'm very much focused on sustainability in cloud and cloud native applications. So that's a little bit about me. When it comes to the more recent work that we've done regarding sustainability, it's the Green Disc certification. It's a digital sustainability certification. It focuses on achieving sustainability in dry labs, if you have a lot of high performance computing, how do you use that efficiently, and so on. Based on the lessons learned, we published a guidebook for sustainability in laboratories, which also covers wet labs, which for us might not be so relevant, but there's also a portion about dry labs. But one thing that always comes back is awareness. Awareness is always the first step towards sustainability. How do you know how sustainable you are when you have no awareness on how big your carbon footprint is, for example? And bringing this awareness to the end user is one of the key things that I've been focusing on in the last 2 years or so. So, since I'm the first one today, I'm going to give a quick recap of the topic of sustainability. So we're all on the same line, we know where we are. 2015 was an important moment for sustainability. Was the time that the Paris Agreement was drafted. In 2016 it was actually signed by almost 200 nations. The goal here is to limit global warming to 1.5 degrees Celsius. So how are we actually doing? We're 10 years along now. This is a map of how far along we are, with green being countries that have achieved their goals, yellow being almost sufficient, orange being somewhere in the middle, and red and black needing to do a lot of work. Well, you can see a lot of orange. So, well, we're somewhere in the middle. That's great, right? Huh? Not great, not terrible. Well, actually, it is not great. If we continue like this, we're on track for a 3 degrees increase in global temperatures. Sure, if we had not done anything, we would have had a 5-degree increase in global temperatures, but we're on this line now. Well, we're supposed to be here. We should be following this trend. Well, we're not. We're not on track. And what does that mean for us? In the last 30 years, we've seen already an increase in sea height variations of 10 centimeters. If that trend continues, then by the year 2100, we can have sea levels change by up to 1 meter, and 1 meter increase. Well, you might think 1 meter is not so bad. Well, I live in the Netherlands. My house sits at 50 centimeters above sea level. I would rather this number be lower than higher. Oh, this is fine. So, that's sustainability on a global level, but how are we doing in IT, in ICT? So the World Bank report of 2024 gives us a little bit of insight into how we're doing on a global scale. This is a graph that shows the cloud data centers and content data centers and their energy consumption. Content data centers being social media related data centers. And we can see that from 2020 to 2022, we've gone from 55 terawatt hours to 85 terawatt hours. So we're still consuming more and more and more energy in data centers. This example is specifically for Ireland. Ireland is a unique case because in Ireland the tax rules are very profitable for companies to settle there, especially for big data centers. And we can see in 2022, 18% of Ireland's energy consumption was associated to data centers. If this trend continues in 2030, 30% of Ireland's energy consumption will all be taken up by data centers. These are huge numbers. So let's look at global scale again. The world energy consumption for ICT as a whole was around 1,000 terawatt hours, 1,100 terawatt hours in 2020, and almost 1,200 terawatt hours in 2022, increased by almost 10%. If we look at the emissions though, they've gone down. So from 2020 to 2022, the carbon CO2 equivalent emissions have gone down. So overall that is good news, right? We're doing pretty good. Again, in 2022, at the end of 2022, we had the release of ChatGPT. And then I can only start wondering what kind of effect will that have on energy consumption. Right, we had in 2023 an AI boom, specifically a generative AI boom. Google Trends went crazy on the topic of AI. This is 2022, 2023, and you can see it just skyrocketing. Also investments in generative AI. 2022, well, around $3 billion in US dollars of investments a year. 2023, 25 billion. 25 billion. So I'm really curious to see, once the data becomes available, what is going to be the impact of these last 2-3 years on our ICT footprint, on the ICT energy consumption. The data is not there yet, but I do read quotes like this. NVIDIA servers dedicated to AI could consume 85 to 134 terawatt hours of electricity every year by the year 2027. The Netherlands, as a country, consumes 113 terawatt hours per year. So you actually wonder, in what direction are we going? What's going to be, the damage we've done in the last few years? Okay. Before we continue, I want to a little bit set the stage and talk about what I do at the Digital Lab and how this relates to sustainability. And the research that we've done in the last 2 years. So, Digital Lab is a team of educators and engineers that focuses on bringing innovation to the university's curriculum by designing and developing a digital tool suite to support education activities. So we're really an education-focused team, and we try to automate certain tasks in education so that we can make education more scalable. In 2023, when I started building the team, we supported 19 courses at the University of Groningen. And then now, at the moment, we are at 55 different courses that we support. And this support comes in basically 3 flavors. There is TEMIS, that's our tool for the automated assessment of programming assignments. Students send their programming assignment there, it's evaluated automatically, student gets feedback. There is repository management. We use this to organize student source code repositories in an automated way. And then there's virtual labs, a way for us to give virtual resources to students in case their laptop is not sufficient. Let's talk a little bit about what this looks like and where we want to go with this. So we're building this microservice architecture, and the ultimate goal here is to be able to specify your course that you're teaching as code. So you declaratively say, what kind of services do I need when I'm teaching my course? And then our platform will be able to transform those declarations into actual facilities that you can then use in your course. That is where we want to go. This is what TEMIS looks like. Students can log in on TEMIS. They can upload an assignment that they've been working on. Then once they submit an assignment, TEMIS will start doing a number of checks, and the students can see, well, how well have I done this assignment. In this case, it says 100% score, so in this case the assignment has been well made. The student can then see all the tests that have been passed, and they can also see the tests that are failing, so the student immediately gets feedback. And this is also useful, of course, for the lecturer, because they can see immediately how well students are doing on certain assignments. So here we have 3 assignments. In the first column, we can see, well, that assignment is pretty well made. In the third column, that assignment is also well made. But the second column is an assignment where students are having difficulties. And where we would like to go is measuring the carbon footprint of these submissions. So when a student does a submission to TEMIS, we want to see what was the carbon footprint associated to this submission. Then there's also virtual labs. Well, some of you might remember computer labs like this. These are some Apple IIs, I think. Others might be more familiar with these kind of computer labs. But we're now moving to a different type of computer lab, and those are the virtual types of computer labs. This is the university's high-performance computing data center. We have 700 CPU cores available here, 6 terabytes of RAM, a number of high-end GPUs that we all can allocate to students, for example, when they need to work on certain assignments. We use this for courses like cloud computing, where students get access to the underlying platform, the underlying cloud platform, and can then develop their own cloud-based applications. We use this for pattern recognition, where students can submit jobs to our GPUs. We use this for web engineering, when students need to develop a web application that then needs to be deployed using CI/CD. We also use this for courses like ethical hacking, because you don't want students to start hacking university's infrastructure. No, you want this to be isolated. And this is something we do with our virtual labs. We can create these isolated environments where students can do what they need to do without endangering the rest of the infrastructure. If any of this sounds interesting, now is the second commercial break of SummerSOC. We are commercializing all these products, so if you are interested in any of this, come find me after the presentation. That's the end of the second commercial break. So, virtual labs. How do we do this at scale? Because we have courses with hundreds of students. And the way we do this is by leveraging OpenStack. It's a infrastructure as a service platform. Then we provision this infrastructure as a service platform with Terraform to deploy our virtual machines. And then we provision Kubernetes on top of these virtual machines. So we're building a Kubernetes cluster. And then on this Kubernetes cluster, we run the actual workloads. Right, so there's many different layers. You have OpenStack, virtual machines, you have Kubernetes as an orchestration platform, and then the actual workloads are running in containers. So how do you measure the footprint of those containers? Because we would like to bring awareness to our students on their carbon footprint. So that is one of the big questions that we've tried to find an answer to, how to do this at a large scale. Because when you have a traditional deployment model, where you simply deploy software on bare metal, it's easy to determine how much the energy consumption of your software was that was running on bare metal. If you go for a more virtualized deployment model, okay, this already becomes a bit more difficult because these virtual machines don't know what's happening on the bare metal. That's the whole idea of virtualization. You want virtual machines to be unaware of what is happening on the underlying layers. But if you go to a cloud-native environment, this is even more difficult. You have bare metal. In our case, that's OpenStack. You have virtual machines. In our case, QEMU. You have the orchestration platform on top of that, Kubernetes. You have containers. There are Kubernetes pods. And then you finally have the software of which you would like to monitor the carbon footprint. So there's a lot of layers of interaction. And how to get the footprint and the energy consumption at the top of the stack here, that is something we've been focusing on in our work. So that brings us to our first publication. This is something that we submitted to ICP 2025. It was titled Understanding the Energy Consumption of Cloud-Native Software Systems, a work that we've done with one of our students, who by the way now works full-time for my team, which is great. The key questions here are, what is the relation between load and energy consumption in typical cloud-native applications across different abstraction layers? How can cloud applications energy consumption be observed using existing solutions? So what tools are out there already that we can reuse? And what level of accuracy can we obtain when we reuse those existing solutions? Why do I want to do this? Well, first of all, profiling. As a software developer, I think it's good to know how efficient your software is. And not just efficient in time, but also efficient in carbon footprint and energy consumption. Then there's billing. We will have a multi-tenant infrastructure, and we would like to bill accordingly. So our tenants pay a fair share of what they're using. And then finally, there's of course sustainability and bringing awareness to our end users. If we can do this, then we can also inform our end users, okay, well, you use this piece of software for so long, and this is the carbon emissions associated with the runtime. So first step is identifying what software tools are already available. Again, we look at the same layers I just mentioned. We have bare metal, OpenStack, virtual machine, Kubernetes, and the software layer. We look at collecting resource usage, so typically utilization of the system. And we look at collecting energy consumption. So then you get a table like this, where you have a lot of tools that we inspected, and then columns for each of the layers: bare metal, OpenStack, virtual machine, Kubernetes, and app. You can see that for bare metal, there's quite a few tools available. For OpenStack, there are resource usage tools available, but for energy consumption on OpenStack, there is simply nothing available. So that is something we already hit as a first obstacle. Then for virtual machines, there's plenty of ways to get the resource usage and energy consumption. For Kubernetes, there's also plenty of ways. At the application level, however, there are no out-of-the-box tools that you can just use to get the energy consumption of your application. These all need to be fine-tuned or are more connected to the bare metal layer. So then we selected for each layer our tool. For bare metal, we use Node Exporter. OpenStack was a special case. If you really want to torture a student, make them set up OpenStack in a clustered environment. It is a nightmare. There are 3 ways to deploy OpenStack, 2 of which are broken, and 3 of which are completely undocumented. So it's not that easy. Then on the virtual machine layer, you have Node Exporter as well. For Kubernetes, we use cAdvisor. And then for the software layer, we use OpenTelemetry. For energy consumption, we have REPL on the bare metal. Nothing was available for OpenStack. Scavander for the virtual machine layer. Kepler for Kubernetes. And again, for software, there's no out-of-the-box tool that you can use for this. These 3 tools, REPL, Scavander, and Kepler, are important. They're going to come back a few more times in this presentation, so I want to highlight them in a bit more detail. REPL was developed by Intel. It was initially developed to enforce power limits of the system. But a nice side effect of REPL is that it also does reporting of the CPU energy consumption. Specifically, it reports the package energy consumption, the package being the whole CPU package, including the cores, the cache, integrated graphics, system agent. It reports the energy consumption per core, so per individual core you get an energy consumption. It also reports energy consumption for anything that is not core, which Intel calls uncore. So that's your cache, your integrated graphics. And then finally, you also get some statistics about your DRAM. So it gives quite a lot of low-level system information. That is REPL. Scavander has two purposes. You can use it to monitor the energy consumption of bare metal, or you can use it to monitor the energy consumption of virtual machines. It has 2 modes of operation. But in general, what it does, it simply uses REPL, what we just discussed, and then it looks at, well, how much is a virtual machine on the host machine consuming, how much utilization, and then it does a mapping from utilization to energy consumption. These metrics are then exposed to Prometheus. And then finally, there's Kepler, the Kubernetes efficient power level exporter. This is used to calculate the energy consumption of pods and nodes. So pods are basically your containers, and nodes are the virtual machines, the machines that make up the cluster. Kepler consists of two important parts. A part to collect performance metrics. This uses an extended Berkeley packet filter to get kernel level metrics. And then it has a number of energy sources it can use. Well, again, REPL, it comes again here. That's one way to get that's one energy source you can use. You can also use external energy sources. If you have an external monitor on the power plug, for example, you can use that. You can use GPU as an input for energy as well. And this is an important one. You can also use models. So there are some pre-trained models that Kepler has, in case you don't have access to REPL or to hardware monitors. Then you can use one of those pre-trained models to estimate the energy consumption of your pods. This is the one that we use in this work. We use the pre-trained models because remember we have many layers. We have bare metal, virtual machine, and then we have Kubernetes. That means that on the Kubernetes layer, you don't have access to bare metal applications like REPL. REPL only works on bare metal, so we have no other choice than to use the model. And then if you combine the performance metrics and energy sources, Kepler will convert them into energy usage. In addition to that, we use what we call a very naive consumption mapping, energy consumption mapping. This is just a sanity check. We calculate the VM energy by looking at how much is the utilization of the VM, and then proportionally mapping it from the bare metal energy consumption. We do the same for pods. It's just a sanity check to see if the values we get make sense. Why can we do this? Well, if you look at your power draw of a CPU, and you look at the utilization of the CPU, you can see this line is pretty much linear. And that's why we can use a simple model to do this sanity check. The system under test, unsurprisingly, there's OpenStack on which we deploy virtual machines. On these virtual machines we deploy a Kubernetes cluster. On this Kubernetes cluster we deploy several pods that are running an OpenTelemetry demo application. The OpenTelemetry demo application is an application that is often used in this kind of benchmarking. That is why we use it here as well. This is what the system under test looks like. Everybody loves Lego. It's 5 i3 Intel i3 NUCs and 4 Intel i5 NUCs. Then we have physical power meters connected to each of the systems. And that way we always have the ground truth. We don't have to rely on software to determine the power consumption. Now we have physical hardware meters. So we then collected a large data set consisting again of those many layers that I already discussed a few times now. For every layer we collect the energy consumption, we collect the utilization, except for the application layer that is a bit different. This is quite a unique data set because this kind of data set does not exist anywhere else, where you have these layers, you have energy consumption per layer, and you have a real application that is running and has some load being put on the application. This data set is open access, so you can also use it in your own research if you want to. After collecting this data, we ran several experiments. We had the constant load experiment, where we had 6 different levels of constant load on the application. So we just put a number of requests through the application at a constant rate, increase it, 6 times. No auto-scaling here. Then we had the linear load experiments, where we had a linear scaling of the load on the application, but with auto-scaling. So as the load goes up, we spin up more and more pods, and then we see what is the effect. And then finally, we have the direct load, where we simply spin up pods that have a stressor running inside the pod, which has a fixed load, so we have full control over the exact load that we want to generate on the system. And then we linearly scale this experiment by spawning more and more pods, every pod adding 200 milli-CPUs of load to the system. So I'm just going to highlight some of the interesting results. If you want to see the full results, look at our paper. First question, how accurate is REPL? We see REPL a lot, I've mentioned it quite a few times now. But when we look in practice, REPL reports an energy consumption, power consumption between 20 watts and 30 watts. But when we look at our physical power meters, it's completely different. We can see the same shape of the data, but the actual power that is reported is between 10 and almost 40 watts. So if REPL is already inaccurate, well, that doesn't bode well for the rest of our systems, right? So, conclusion, we see the same shape of distribution, but we see a completely different scale of the values. Then we go to Scaphander, the tool we use on the virtual machine layer. There we see also very strange behavior. So the top one is our naive approach. This is our sanity check. And we look at how frequently we see certain values. How frequently do we see 5 watts? How frequently do we see 15 watts, etc. If we look at how the frequency is on Scaphander, we see really strange binning of these values. There are really high spikes for certain values. We were not able to figure out why this happens with Scaphander, but again, it doesn't match what is happening in reality. So also Scaphander has its issues. So here the distribution is just completely different. However, there is some hope for Scaphander, because if you look at the average values, on average it does follow the same line more or less. Green here is Scaphander, blue here is our naive consumption mapping for virtual machines, and we can see, well, okay, sure, it gets somewhat close, and the shape is the same, but it's not perfect. Here's a lot of data. Don't pay too much attention to all the lines. I just want to talk about Kepler here. All these other lines, they're quite similar in the way they change over time. But there's one that stands out here. That's the red one. Well, can you guess which tool the red one is? Yes, that's Kepler. Kepler is behaving completely erratic, spiking up and down. There's no rhyme or reason to it. And there's something funny going on, because Kepler attributes power consumption to pods that are idle. So you have pods that are not doing anything, but they get, by Kepler, assigned some power consumption. Completely strange. Okay, so to summarize, we have a lot of tools for monitoring that we can use, but the tools are inaccurate. REPL, inaccurate. Scaphander, sort of close, but there's a real strange distribution of data. And then there's Kepler, which behaves very strangely, and we'll see a bit more about that soon. And this is on a private cloud, right? This is a cloud that we set up. We have full control over every layer. How would you do this in a public cloud, where you don't have access to the bare metal layer? And then, well, we thought, well, we need to figure out what is going on with Kepler, because what is happening there was completely strange to us. So that is what we did in the next work. This is a work we submitted to ICT4S this year. It's about understanding container-level energy observability in Kubernetes clusters. And this continues the work that I just presented to you. This is again a work we did with one of our students, and it focuses really on the Kubernetes and Kepler parts. So we saw a lot of anomalies in the data from Kepler in the previous work, and then we started looking into other evaluations of Kepler, and we found that there is no systematic evaluation of Kepler anywhere except for an initial evaluation that was made when Kepler was basically created. Despite all this, Kepler is used quite widely in a number of publications. So this brings us to the central question here. How can we accurately estimate the power usage of Kubernetes containers based on measurements we do external? So these are measurements from power meters, measurements from the out-of-band management interface of the server, those kind of measurements. The experiments here we designed as follows. We have a Kubernetes namespace, and in that namespace we create, we have Kubernetes namespaces, and there we create two separate namespaces, a stress namespace and an idle namespace. In the stress namespace we start in a stressor pod. This pod just runs a constant load that we can configure, so we have full control over it again. The idle namespace is where we introduce those idle pods that I mentioned earlier that were exhibiting quite some strange behavior. So these are pods that have completed, so they have the state completed in Kubernetes, but they've not been deleted. So the containers are still there, but they're not doing anything. Then once we set up these namespaces, we deploy Kepler on the cluster. We use two data sources. One is called iDRAC. That's the out-of-band management software that Dell uses. And we get the platform power from that. And now we use REPL data again to get the core and package power. The ground truth here is iDRAC data, because that is very accurate, whereas REPL, well, we've seen what REPL can do. This is the system under test. It's a Dell PowerEdge server, has 32 cores. On this system under test, we deploy Kubernetes, which then has Kepler and cAdvisor running in the cluster. cAdvisor we use to collect the utilization of the node, so how much memory, how much CPU is consumed by the node and by the pods. And then we deploy on a separate thin client, we deploy Prometheus. All data goes to our Prometheus database. Then we can of course visualize that with Grafana and so on. We also have the iDRAC exporter to get this ground truth data from iDRAC into our database. And that is the test setup that we have. If we then look at the data, how accurate is Kepler using bare metal data? Well, we can see that it seems to be pretty accurate when we look at the totals. There is, so if the orange one is iDRAC, so that's the ground truth. The blue one is Kepler. And we see there is some delay in the data, some lag, but otherwise, well, it's pretty close. But as soon as we start looking on pod level, the picture changes again. This is what the results are on the pod level. This is our first experiment. In this experiment, we create a stressor pod that runs for almost 5 minutes, I believe. And then after that, it stops for a minute, and then it starts again for 5 minutes. This purple line is the stress namespace. And you can see the power draw of the stress namespace becomes quite high when the stressor pod is active. But there is something strange going on, because we see the experiment ends. The power draw of the stress namespace is 0. But suddenly we see a huge spike in all the other namespaces. Well, nothing is happening there. Why is it being attributed to all this power consumption? That's strange, right? And we see this again when we repeat the experiment for the second time. We see again a spike in the other namespaces. So as soon as the stressor completes, the other namespaces, they peak. And there's also something weird going on with the idle namespace. Maybe you've seen it already. The idle namespace is the orange one. This is the idle namespace. It has a continuous power draw of almost 100 watts. But there's nothing running there. Why is it being attributed to 100 watts? So again, this really shows that Kepler is doing some strange things under the hood. Then we do a second experiment where we see even more different behavior. In this case, we create 64 idle pods that are there from the beginning. So at TS0, there are 64 idle pods. Then in this the second line here, we delete all the idle pods. So they're no longer in Kubernetes, they're completely removed. What we see then is that as soon as we delete these idle pods, suddenly we have another namespace that spikes. This is the system namespace. Why would the system namespace spike when we remove pods that are not doing anything? And why would it spike higher than the stress workload we've put on the system? That's the purple line. Again, very strange behavior by Kepler. So, what we did as a sanity check for ourselves was develop our own proof of concept to see if we can do better than what Kepler is showing us, or if this is maybe a problem, or maybe this behavior is simply part of the problem. So we designed CubeWatt, which divides power draw into static power and dynamic power. Static power being the static power consumption of the node that is always there. Dynamic power is the power that is associated with the workloads running on the node. We introduced two initialization modes to CubeWatt. These initialization modes are important because first of all, it determines the static power of the node, and second of all, it trains a linear power model that we then use later to estimate the power consumption per pod. There are two ways we can do the initialization. One is using an empty cluster. So you start with a fresh cluster, nothing is running on there. In that case, it's really easy to get the static power. You simply wait for the cluster to stabilize, you start monitoring, and you see what on average your static power is. Easy. But of course, you don't always have an empty cluster to work with. Sometimes you have an existing cluster. In that case, we introduced a way to initialize when you have an existing cluster by monitoring for longer periods of time, and then trying to gather as much data as possible and stopping when we have enough variability in the data to determine what is the static power. So here, CubeWatt again, we use iDRAC as our power source, our ground truth power usage. Then we connect the Kubernetes metadata about how many nodes are in the system, how many pods are running in the system. We connect cAdvisor also to CubeWatt, and then CubeWatt collects all these metrics and calculates the power consumption, both the static and the dynamic power, which is then again inserted into Prometheus. This is an example of what it looks like when we run CubeWatt in an existing cluster. This was quite an active cluster, so there was not much time in the cluster where the utilization of the cluster was low. So it took quite some time to gather enough variability in the data. In the extreme case, we had to wait 13 hours for enough data to be available. The nice thing is, it then estimated the static power to be at 198.44 watt, where iDRAC reported static power as 199.1 watt. So we were very close to the ground truth. So this initialization works, but it takes a long time for it to be completed. Then, based on the data we collect, we fit this linear model. We get an R squared of 0.92. So it's a reasonably good fit, especially for the lower values. We see some more spread around the higher utilization values. The nice thing is, once we have this model, we no longer need the ground truth data. So the iDRAC data that we saw in the previous slide, this one, we no longer need it. So we can get rid of it. That means that even if we were running it into an environment where we did not have this ground truth data anymore, we could still use CubeWatt. So, how does CubeWatt perform? Here we see the CPU utilization of the different components in the namespaces. This purple one is again the stress namespace. And you can see that every other namespace is pretty much using no CPU here. It's only the stress namespace that is responsible for the load on the system. And then we see the power consumption over time. All of these 0 watt namespaces, they're all bundled in the static power. So what you can see here is the stress namespace. We start our experiment here. We basically repeat the same experiment we did before. We run a stressor. At this time we delete all the idle pods, because again we have those 64 idle pods still somewhere. And we see that we don't have any weird behavior, no strange spikes. which basically shows us that the behavior that Kepler is exhibiting is not inherent to the problem. There's ways to solve it. And while this might not be the most accurate way to do it, it does show that this does not generate those abnormalities where idle pods are attributed power consumption. So a key finding here, Kepler is accurate at the cluster level, but not at the pod level. And QPlot shows that we can make a simple proof of concept that addresses some of Kepler's shortcomings, and then we see this is not inherent to the problem. Then we come to the last slide, where I want to give a little bit of a look ahead of what we'll be working on next. So initially we set out to build a monitoring stack using existing technologies, existing tools that were aimed at large-scale cloud-native deployments to bring awareness to our end user. We wanted to communicate to our end users, what is your footprint, what was the energy consumption of the workload that you just ran. But we saw also that the key technologies that we investigated have some critical flaws, right? REPL, it's inaccurate, completely wrong scale. It reported the value between 20 and 30, while it should be between 10 and 40 watts. Scaphander, on average it was quite close. But the distribution of the data, it was completely different. And then in Kepler, we saw two problems. We saw that there was lag in the data, and we saw that Kepler does not know how to deal with idle pods. Pods that exist on the system but are not doing any work. So, we proposed QPlot, an open source tool that you can also check out yourself, but this only solves a small part of the puzzle, right? Because QPlot works on the Kubernetes layer. And all of this work was evaluated on private cloud, while you will not always have full access to the bare metal layer of your cloud infrastructure. So that leaves us with the final question. How can we achieve true full stack energy monitoring of cloud-native applications on public and private clouds? And I think that is an important question to answer. A question we don't have the answer to yet, but hopefully in a year I'm back here presenting you a better way to address this problem. Thank you very much for your attention. I hope you learned a thing or two about sustainability in cloud-native systems.
Questions?
Thank you, Brian. First, a technical question. For the application, you cannot use code carbon because you don't have the source code of the applications? Or?
Because we don't have the source code of the application, and the application itself runs on so many layers of virtualization that you need the data from somehow you need to propagate the data up to the application layer. In our deployment specifically, we use cloud infrastructure that is provided to us as a platform. So we don't have access to our bare metal layer, and that makes the problem much harder because we don't know what is the actual ground truth because we cannot monitor it. So we will need to have a way to model this first layer, the bare metal layer, and only then can we start propagating up and up and up until we reach the application layer.
And then the second question is about your research question. You say, how can we? I would rephrase it, can we? At all?
That is a good question. I think we can. I have a feeling that we can do it. But I think it requires specific solutions for each layer. I think we need to find a way to propagate some of the information from the lower layers to the higher layers of abstraction. And I think then we can really achieve full stack monitoring.
For private clouds, yes. For public clouds, there's also active trying of masking that, right? So they don't want you to know what's going on. So I wonder if you can only estimate up to a certain accuracy what's going on.
Of course, you will need the public cloud to collaborate with you. If they don't, then well, there's nothing you can do about it.
Yeah, I think it's going to be hard. Because the trend is like what they're saying now is to put little nuclear power plants next to the data center. So we forget about measuring, we just put infinite amount of energy,
Yeah.
power available.
Yeah.
Thanks.
The last comment brings me to my question, namely, there is a difference between energy footprint and carbon footprint, right?
Yes, correct.
And there are these two dimensions that are of interest here. One is the embodied carbon that is in the bare metal, right? The production carbon. And the other is that indeed there are different sorts of energy, and some, I'm not talking nuclear, I'm not talking solar, but would even discuss nuclear. Some come without a CO2 footprint except for the embodied, right? And so, I mean, since you are doing this very detailed analysis, you should also look at what time of the day is it happening, where is it happening, what is actually the energy profile, the rate that is used there. Is it, you're just not mentioning it because it's easy, or?
So if you would have accurate measurements on your full stack, you could accurately monitor the power consumption and energy consumption, then converting this number to a carbon footprint based on the data that's already out there, because there are European platforms that give you an estimation of the footprint as accurate as it is.
It depends on the time of the day then?
It will depend on the time of the day, if there's a lot of wind, if there's a lot of solar. But if we cannot even measure the energy consumption of our stack, then how are we going to accurately measure the carbon footprint? But I completely agree with you.
The question is whether you have to accurately do this. The question is whether averaging doesn't help you. Like you were doing this, you were going away from the pot, you were going to the clusters and so on. This was averaging basically.
Yeah.
And the question is whether you wouldn't want to do this on a larger scale. So, which at the end would mean you look at the code that the person submits and you analyze the code, and the rest is just averaged. I mean.
Yeah. In that case, yeah, you might get an average that gets sort of close, but how do we measure that this is indeed close to the ground truth if we cannot even get the ground truth for all of our layers? So I still think there's a lot of work to do for each of the layers, and then maybe we can test that hypothesis that an average might be enough. But for that we do need the other parts of the puzzle to be solved.
Okay.
More questions? Okay, with that I would say that we can again applause again to. And it looks like we have to wait for more results, for a year. But I would say that the first 15 minutes of that waiting we can do outside during the coffee break, and be back at 11:15 for the second talk of the session.